Hello and welcome to this Python, Data Science and Machine Learning mini course from Data Science Infinity. This mini course has already been taken by thousands of students, career transitioners, and those already in the field. Many of these students have gone on to fall in love with their new skill set and have used it as a springboard to move onwards and upwards into great roles in the exciting, future-proof, and lucrative field of data science. Very quickly to introduce myself, I am Andrew Jones and I will be taking you on this short but fascinating journey. I've been working in the areas of analytics and data science for over 14 years, but my journey to where I am now is a little bit of an odd one. So I didn't study data science or computer science or even mathematics at university. Instead, I did degrees in marketing and psychology, and I actually just happened to land my first role as a marketing analyst simply through playing cricket with the manager of that team. In this role, I started using a programming language called SAS, and I was blown away with how you could not only manipulate and analyze data, but how you could use machine learning to predict what customers were going to do. I was hooked, and I've been so passionate about it ever since that I've continued learning and moving into different roles in different industries, and in recent times I've been fortunate to have worked for Amazon as well as Sony PlayStation, where I built and prototyped machine learning based features for the PlayStation 5, several of which have been patented by Sony. Now, the aim of this mini course isn't to get you to any particular level of competency within any of these areas. It's really a way to show you that starting this journey is 100% within your reach. So let's do this. Over the next couple of hours, we are going to learn about the Python programming language. We're going to install Python and investigate the basics of coding in it. We're going to use a Python package called Pandas to explore and analyze a dataset, one of the fundamental day in, day out tasks that a data scientist or data analyst does. Then we will move on to our first exciting project. Together, we're going to write around 7 or 8 lines of code where we will loop through some logic over and over again until it searches out and finds all the prime numbers that exist under 1 million. And this is going to be so cool because it will do this in somewhere around half a second. This is going to hopefully give you a glimpse into some of the more interesting and amazing logic that you can use within Python. From there, we're going to start our journey into machine learning, where we are going to discuss the broader field and its applications, take a look at the high-level theory behind one of the most popular machine learning algorithms, the random forest, and then we're going to jump into Python and build, test, and train our model that will predict how long it will take certain video game players to complete a particular challenge in their game, based upon their level and the amount of ammo that their character has. This is going to be really cool, so let's not waste any more time. Go and get your coffee ready and let's make a start. In the next tutorial, we will take a quick look at the Python programming language, what it is, where it came from, and the extraordinary breadth of amazing tasks that can be done with it. I cannot wait for this. I will see you there. Hello and welcome to this tutorial where we are going to discuss at a super high level what Python is, where it came from, and what it is commonly used for. Now, after this, I'm going to walk you through how to install Python onto your PC so we can get into some actual coding, and this is very exciting. But before getting into it, it is important to understand a few basics around this programming language. So let's jump right in and start at the very top, discussing what Python actually is. At the highest of levels, Python is simply an extremely popular programming language. And to take this back one level further, a programming language is essentially just a language that we can use to provide the computer some instructions which it will then carry out. There are a lot of different languages that can be used, but the more you use Python, you start to learn that you can pretty much do anything with it. It really is incredible. Not only is it really functional, but it's renowned as one of the easier programming languages to learn, to read, read, to understand, and to use. Of course, the use cases can go from the very simple to the extremely complex, but overall, the way it all pieces together is very intuitive. So it's really exciting that we are going to be getting started with it together here. Now, before we get into some of the amazing things that can be done using Python, I'd quickly like to mention where it came from. So Python was created by a Dutch man named Guido van Rossum and was first officially released way back in 1991. So while it's getting on in years, its popularity has really exploded in recent times due to its use within data science. And as it's been around for some time, it has evolved over many versions, with Python 3 being the latest high-level version. Although, as you'll see when we get to installing Python onto our machines, there are sub-versions such as 3.7, 3.8, and 3.9 that are released more frequently. It's worth noting that as of the 1st of January 2020, Python 2 is no longer being supported by the Python Software Foundation. If you progress further into programming or data science after this course, you may very well come across old codes or scripts that are using Python 2. And while the vast majority of the syntax is the same, there are some changes and improvements since then. So we will be working solely with Python 3 in this mini course. So that is an extremely high-level overview of where this programming language came from. Let's now discuss what exactly we can do with Python. And like I mentioned before, we can really do almost anything. We can do data analysis, so exploring and manipulating data. In Python, a library that you will come to know and love for this task is called Pandas, and we will be using this once we've got Python up and running. We can also very easily visualize our data using all sorts of plots and charts. Remember the name matplotlib. Like Pandas, if you keep working with Python in the future, you will come to know this very well. We can undertake all sorts of data science and machine learning related tasks, whether it be understanding or modeling tabular data, image data, audio data, or any other type of data. We can do it all in Python. Taking this further, we can build deep learning models, in other words, the latest and most advanced modeling techniques using neural networks. There are several libraries that are primarily aimed at making all of this nice and easy for us in Python, namely TensorFlow, Keras, and PyTorch. There are also dedicated libraries for computer vision, and one in particular called OpenCV that helps us deal with any image or video data that we want to modify, manipulate, or process. Similarly, we can undertake tasks in the realms of natural language processing, or what is often simply referred to as NLP, where we are dealing with understanding, processing, and even creating text data. There have been huge advances in this area in recent times, so this is a really exciting field. Underpinning a lot of the topics that we have just talked about is statistics and just mathematics in general. There are packages devoted to this in Python, and these are very commonly utilized in pretty much all of data science and machine learning. Taking a slight tangent, Python is also great for web and app development. If you want to build a website or an app for your phone, then you can actually do this using some clever packages and libraries in Python. In fact, some very large companies, including Spotify, Netflix, and Instagram, all have their web foundations based in this way. Not only can you create web-based applications, you can also create games. How cool is that? We can also scrape data from websites and social media platforms for us to analyze at our leisure. And of course, as Python is a programming language, we can automate and script any inane tasks that we find are taking up too much of our time. As I say, it is an extremely versatile language, and I guarantee you are going to grow to love it. So without further ado, let's get practical. We are going to be utilizing a platform known as Anaconda, which, as you'll see when we get there, installs Python itself as well as an IDE or integrated development environment called Spyder, where we can write all of our code. Anaconda also installs Jupyter Notebook, which is another way that we can write our code, but in a web-based environment. Anaconda also pre-installs all of the commonly used packages that are used in data science. So it's essentially a complete, more or less ready to go Python solution for us. This makes it great for data science and great for this mini course. In the next tutorial, we will install Anaconda and get ourselves in a position to start coding. I am super excited about this, so I will see you there. Hello and welcome to this very exciting tutorial where we are going to install everything we need in order to start coding away in Python. As I mentioned at the end of the introductory tutorial, in this course we're going to be utilizing a platform known as Anaconda. Installing Anaconda will not only install Python itself, but will install virtually all of the packages that we need for data science. It will also install Spyder as well as Jupyter Notebooks, giving us two awesome places to write and edit our code. Let's jump right into this and get it downloaded so we can get stuck into some Python. Alright, so picking your browser of choice, let's search for Anaconda Python. Your results may be slightly different to mine, but the result that we are looking for is this individual edition of Anaconda. This takes us to a page that tells us all about the open source, in other words, free edition of this platform. Companies can pay for enterprise and team editions, but individuals like you and I can get everything for free. Once you see everything that is included with Anaconda, you will be blown away that this is all free to use. It really is incredible. Let's scroll down and take a bit of a look. Here we see a selection of packages and libraries that will be installed alongside Python. We have Jupyter Notebooks and Spyder for coding, SciPy and NumPy for all of our mathematical operations, scikit-learn for machine learning, Pandas for data exploration and manipulation, matplotlib for all of our visualization needs, and even TensorFlow and PyTorch should we want to delve into the world of deep learning and neural networks. If we keep scrolling down, we will eventually get here, where we have the option to download Anaconda for our specific operating system. I'm downloading for a 64-bit Windows machine, so I will be downloading this one here, but you can simply choose the one that's right for you. Once we click this link, it should start downloading automatically. Once downloaded, locate the file on your file system and open it. This will start the installation process. We will essentially just be following the default settings throughout the installation, so we can just continue through the process without needing to change anything. The installation will take a little while as it is quite a large file. Feel free to pause the video here and you can continue on when you're all ready to go. Once installation is complete, we can hit next and next again. Since we're going to be learning about Anaconda here, I'm going to uncheck these two boxes and hit finish. Now that the installation process is complete, there is one key application that we are really concerned with, and that is called Anaconda Navigator, which you'll be able to find by searching through your programs either using the Start menu in Windows or the Finder on Mac. So let's open that up now. Anaconda Navigator is essentially a nice, easy to use front end for all things Anaconda. Within here, we can open up our coding tools such as Spyder or Jupyter Notebook. We are going to be using Spyder in this tutorial, so let's click that icon and open it up. Now, Spyder is what's called an IDE, or an Integrated Development Environment, essentially a front-end tool to help us write and edit our Python code. Spyder stands for Scientific Python Development Environment, and in my view it is one of the best as it's been made specifically for Python. When you've opened up Spyder, you should see something more or less like what I have got here. If yours doesn't look exactly like mine does, then don't worry. You can toggle which panes are available by going up to the top to View and Panes, and all of the key ones will be there. The ones that we want are the editor here on the left, which is where we will write our code and which shows us the Python file or files that we currently have open. When we open up Spyder for the first time, it gives us a temp.py file like we see here. Otherwise, it should just open up the files that we had open last time we used it. And it's worth noting that Python files do have this extension .py. Since Spyder has been built specifically for coding in Python, it will automatically save files with this extension. And we can save our script as you'd expect, just going up to File and Save or Save As. If you wanted to create a Python file outside of Spyder, it's as easy as saving a text or notepad file with .py at the end. If we do this, then any Python application will be able to understand and run it. We will also want the IPython console down here at the bottom right, which will show us the results of what is happening each time we run some code, including things like error messages and warnings, and you'll see this in action as we go. On top of that, we also want some useful panes which we can see here in the top right. Here we have the Variable Explorer, which is where we can investigate any objects that we create while coding. If we head over to the editor, and I'm just going to zoom in a little bit to make my code a bit bigger for you to see, and I was to simply code x equals 10, and then on the line below y equals, in quotation marks, Python, and I was to hit the green run button up the top here, we can see that our two objects appear over here in the Variable Explorer. Here you can see that x is of type integer or int, and y is of type str or string, which is essentially what we call text objects in Python. We'll be quickly covering off all sorts of different and useful data types and structures in the next video, but this Variable Explorer here is where we will be able to investigate them and see them as they are created. The next tab across after Variable Explorer is Files, and this is where we can view the Python files and any other files that we are using on our hard drive. Now we can point this to any folder location that we want, and this is what is known as our working directory, and we can do this by hitting the folder icon up the top here and selecting a folder. If we had our Python script and some other data that we were using all in one folder, we would point Spyder to this, and it would mean we'd be working right in that directory, making importing any data really easy. Over on the far right of these tabs, we have plots, and this is where any charts or visualizations would appear if we were to create them in our code. Now, one great thing about Spyder is that we have the ability to just run any highlighted pieces of code that we want, rather than always just running the full script as in some other IDEs. In our code over here on the left where we created our X and Y objects, if I only wanted to create X, I could simply highlight that line of code and then hit F9, and this will only run this line and nothing else. And we'll be using this all the time during the course, so it's a good shortcut to know. If we go up to Run in the menu at the top here, we can see that we have several options to run different parts of our code, but for the most part, just remember the F9 shortcut for now. Alright, so that is it for this whirlwind introduction to Anaconda and Spyder. In the next tutorial, we're going to get cracking on learning and coding up some real Python. This is super exciting as it is such an amazing skill set to have. I can't wait to get into this, so I will see you in the next tutorial. Hello and welcome to this next video, and it is an exciting one. Here we are going to get our hands dirty and actually code up some Python. So to get prepared for this, please do open up Spyder like I have done here. Before we get started on any coding, I want you to set your working directory to the DSI mini course folder that you created in the set of instructions prior to this video. To do that, we just go up to this folder icon at the top right and then navigate to the folder that we want. And in my case, this is on my desktop, and we click Select Folder. Once this is done, if we click on the Files tab over on the right here, we can see all of the files that exist in there. Since this is currently empty, we don't see anything. We are now going to save our Python script into that folder. So let's head over to the editor and let's actually remove this code here that Spyder gives us by default. And then to save this script, let's go File, Save As, and then we will navigate into our DSI mini course folder, and let's save this script as 001 Python Basics. Perfect. So as I alluded to in the Intro to Python theory tutorial, Python is an extremely vast and popular programming language where you can do almost anything. My goal here is not to try and cover all of that off. Quite the opposite. I want to simply show you the absolute basics at a very high level, and I want to try and make it interesting and fun. So let's get started. So in Python, we can do mathematical processes. So we could do something like 5 plus 6. And if we run that by highlighting that line of code and hitting F9, we can see down here in the console that we are being provided the result of that. So we can see here that we have got a result of 11. And we could do the same for subtraction, multiplication, division, putting one number to the power of another, and so on. And while what we just did was interesting, it would be far more useful if we could store these values and then perhaps refer to them in a subsequent piece of logic. So instead of just 5 plus 6, we could do A equals 5 and B equals 6. And if we run those two lines of code, so let's highlight them and hit F9, we can see down here in the IPython console that they have run successfully. And if we click into the variable explorer, we can see that these objects have been created. Our A object holds an integer value of 5 and our B object also holds an integer value of 6. And now we have those two objects created, we could use them further down our code in subsequent logic. So we could do something like A plus B, and if we run that, again we can see down here in the console that we are returned 11, but we've gone about this in a much more dynamic way. If the value of A changed for some reason, so let's change A equals 5 to A equals 10, then we could just rerun those three lines of code and it would give us the updated result. And this might not seem like much, but it is a very powerful concept. What we could also do is ask questions of our data and then specify certain instructions to be carried out depending on the result or the outcome. So we could do if A plus B is greater than 10. So if that is true, then print a value to the console of high, so a high number, and then we could put else. So if that is not true, print low. So here, all we are saying is if the result of A plus B is greater than 10, then do that first thing, which is to print out the word high to the console. Otherwise, do the second thing, print low. And hopefully this really gets the cogs in your mind going about why something like Python is so powerful. We can put in place logic that operates dynamically depending on what is being passed to it. Now this might seem like a silly example, but imagine a nuclear power plant. You might want to say, if sector 7G temperature is less than 100, then do nothing. Otherwise, raise the alarm. Like I say, an oversimplified example, but it hopefully illustrates how this type of logic could be used. Now, so far we've just been looking at numbers, but we can also store text, or what are known as strings, in a variable. We just need to put quotation marks around it so Python knows that this is what we're trying to do. So we could do something like C equals, and then in quotation marks, Python. And if we run that and we take a look up in the variable explorer, we can see that we have created this object called C, and this time it is of type str or string. Now there are a lot of cool things that you can do with strings in Python, but I actually want to keep working with numbers for now. And I want to show you that we won't always just be using one value at a time like we've done so far with the values for our A and B objects. In data science, we are often working with large volumes of data rather than just single numbers or strings, and we need some type of object, or what is often known as a data structure, to store this data in for the purposes of analysis, modeling, or visualization. There are 4 key data structures in base Python. There are lists, sets, tuples, and dictionaries, and they each have unique properties and purposes that make them appropriate for different scenarios. The most commonly used data structure is the list, and to create one we would just name it like we've done so far. So let's just call this my_list for now, and then to tell Python that we want to create a list, we simply put a set of square brackets, so equals and then 2 square brackets. Within the square brackets, we can put in the values that we want, separated by commas. So let's just put in some random values for now, such as 5, 7, and 2, for example. And if we run that, we can again head to the variable explorer and we can see that we've created an object called myList. It is of type list and it has 3 elements within it. We could append further values to our list using a method appropriately called append. And to do this, we can simply do myList.append and parentheses, and then within those parentheses, the value that we want to add. So let's say that we want to add the value 9. If we run this line of code, we can see up in the Variable Explorer that we have successfully added that number to the end of our list. We can also access certain elements from our list if we need to, and we do this by asking for the element at a certain position or index. In Python, the very first element in a list, which here is the number 5, is known to be at index 0. So if we wanted to access that element, we would do my list and then square brackets, and we would specify the index position that we want. So if we put 0, and we run that line of code, we can see down here in the console that we are returned the value 5, which exists at the 0th position or at index 0. We can also do some simple aggregation or summarization of the data in our list. So I could type sum and then parentheses and my list, and if I run that line of code there, you can see down in the console we're provided the sum of 5, 7, 2, and 9, which is 23. We could also find out other interesting nuggets of information too. So instead of sum, let's put max and my list. And if we run that line of code, we are returned 9, which is the largest value in our list. And similarly, we could run min, and this would return us 2, the smallest value. So that is a little bit about lists. Sets, tuples, and dictionaries are somewhat similar to lists, but they all have their own nuances and their own reasons for existence, which are mainly based around speed, storage, and the ability to access elements easily. Look out for the use of sets when we run our first project around finding prime numbers later in this mini course, as we'll be using some key functionality of this data structure that enables us to eliminate values from one set if those values exist in another set. Don't worry if this doesn't make a whole lot of sense right now, it will all become a lot clearer in that tutorial. Now, since we've got several values stored in our MyList object, I want to quickly show you something else that is really useful in Python and in programming in general, and that is the ability to iterate or loop through the elements. If we type for value in MyList and then colon and enter down to the next line, print and within parentheses value multiplied by value, this is an example of a for loop. And here, all I'm asking Python to do is to iterate through each of the values in our list, and for each of those values, print out that value multiplied by itself. And again, you're seeing this use of the colon and then the indentation on the line under that we saw earlier with our if-else conditions. And this just tells Python what should be part of the looping logic that we are applying. All right, so before we run this loop and see what it does, let's just take a note that the values in our MyList object are 5, 7, 2, and 9. So now we know that, let's run our loop and see what happens. So highlighting both of those lines and hit F9. Right, so down in the console, we see our results. The loop has run through each value independently, and each time it has carried out our instruction to multiply the value by itself and then print that result out. How cool is that? And just to be super clear of what's going on here, the first value in our list was 5. So it extracted that and multiplied by itself and printed out 5 multiplied by itself, which is 25. Once it had done that, it went to the next element in our list, which is 7, and it did the same thing there, and 7 multiplied by itself is 49. And it continued to loop through each of the elements in our list until there were no more elements to be looped through. And what we've done here is a very simple example, but this is such a powerful concept in practice, and it becomes even more powerful when you combine a loop with some conditional logic like we learned about earlier. For example, for each value, if it meets this criteria, then carry out instruction 1, else carry out instruction 2. It's worth noting that there is another type of loop commonly used in Python, and this is called the while loop. And with a while loop, instead of specifically looping through a list of values, with a while loop, we are instead looking to continue looping until some set criteria is reached. And we will be using this logic in the Primes Finder project as well, so keep an eye out for that. Alright, that is all I'm going to cover for now. Believe me, we could talk for weeks or months about what can be done in Python. But like I keep saying, the purpose here is to whet your appetite, not to swamp you with information. In the next tutorial, we will be taking a look at an external package of logic that we can import into Python to manipulate and analyze tables of data, or what are known as data frames. We'll be doing this in the extremely popular package called Pandas. I cannot wait for this. Again, we'll be flying through quickly, but it will be good to see what Pandas can do, and some of the basic tasks that data scientists and data analysts do day in, day out. I will see you there. Hello and welcome to this hands-on tutorial where we will be having a go at analyzing and manipulating a grocery sales dataset using the extremely popular Python package known as Pandas. If you are wanting to work in the data science field, I would say that it is an absolute necessity to know about and to be able to use Pandas, as these types of analysis and manipulation tasks are so common. Just like the last tutorial on base Python, we'll be racing through this quite quickly. Again, the aim here is not to teach you everything. Here, I just want to show you the absolute basics so you can see that this is all within your reach, and to get you excited about the types of tasks that can be done so easily within Python. So let's talk a little bit more about what Pandas is used for. Pandas works on tabular data, so similar to the type of data you'd be used to in an Excel spreadsheet. Rows and columns. Using Pandas, we can import data from many file types, including Excel, CSV, and text files, enabling us to do all of our analysis and manipulation right here in Python. It may be that we need to clean our data. For example, we need to deal with missing values or outliers. We might need to change the format of our data and then export it for use in machine learning models or data visualization. We may need to join or merge multiple datasets together, or we may need to aggregate up key statistics to gain impactful insights for our company. All of these can be done easily and intuitively in Pandas. So like I say, it is essential knowledge to have. So let's get cracking and import the Pandas library. And because we have installed Python using Anaconda, this is all pre-installed for us. All we need to do to bring in the amazing functionality of Pandas into our Python session is to type import pandas as PD. So let's highlight that line of code and hit F9 to run it. And just like that, we have Pandas at our fingertips. And you'll notice that I have used as PD here. This is a common convention in Python when referring to Pandas. We just use this PD alias, and you'll see what I mean as we move on. So now that we have brought Pandas in, let's import our grocery sales data. You should have downloaded this CSV file based on the information in the prior tutorial, and it should be sitting in your DSI mini course folder. If not, please go back and do this, as we will need that file here. And because we want to make everything nice and easy for ourselves, let's make sure we set our working directory to our mini course folder using the folder icon at the top. Once you've done that, save your script into that folder and call it 002 Intro to Pandas. Perfect. Now, to import our file, Pandas makes this really easy for us. We just need to create an object to store the data in. So let's just call this sales_data. And this is going to be equal to PD, our Pandas alias, dot, and then since we are importing a CSV file here, we use a method known as read_CSV, and then we put in parentheses. Since our file is in our working directory, Within the parentheses, we're just going to put in the file name. So within quotation marks, we're going to put grocery_sales.csv. And if we run that line of code and then go to our variable explorer, we can see that we have successfully imported it. We can see that it is of type data frame, which is the data structure used by Pandas. And we can also see that our data frame has 4 columns and 281 rows. If we double click sales data here, we can open that up. And here we can see our data. We have customer ID, transaction date, transaction ID, and a sales value. So this data is the sales data for around 100 customers at a grocery store during the month of September 2020. It is at customer and transaction level. So for each transaction that a customer makes, we have the aggregated sales, so the total amount that they paid at the till. What I would like us to do here in this tutorial is to aggregate up this data by date. In other words, get the total sales for each day within September, and then plot this very simply onto a chart so we can visualize this trend over time. Now, before we close this window down, I want you to notice something. In this 5th row of the sales column here, we have NaN, which stands for not a number, rather than a dollar value like we see in the other rows. And this is actually a row where the sales value is missing. And this isn't ideal. So before we get into aggregation, we want to put in place a really simple solution to remedy this and any other missing values in that column. And if we sort these values by just clicking the column header here and then scroll all the way down to the bottom, we can see that we have 4 missing values in our data. So back to the code and let's sort this out. Pandas has an almost unlimited supply of useful data manipulation functionality, and one of those is called fill-in-a, which will do exactly that. It will fill in any missing values from either the whole data frame or a specified column. We are going to do something fairly simple here, and in the real world you'd probably put a little bit more thought into this, but all we want to do is replace any missing values in our sales column with the overall mean sales value. So if the average transaction value is $50, for example, then we'll replace those missing values with 50. Like I said, to do this, we use something called fill-in-a. Before we apply that, however, we want to calculate the average sales value so we can pass this to the fill-in-a method. To do this, let's first create a variable to store this information in, and let's call that average sales. And this is going to be equal to our data frame name, so sales data, and then within square brackets, we name the column that we are interested. So within quotation marks, we'll put sales. At the very end of this line of code, so after those square brackets, we can just put dot mean and parentheses. And if we run this line of code and then look over to our variable explorer, we can see that average sales has been created and it has a value of just over $56. Now we have this value, we want to use the fill-in-a functionality. And to do this, we can just type sales data and then square brackets and again in quotation marks sales. So here we are specifying the column that we want to apply this to, and then after that square bracket we're going to put dot and the name of this functionality, which is fill-in-a, and then parentheses. Within the parentheses we want to specify 2 parameters. Firstly, value, and we're going to set this equal to our average sales object. So this is us telling the fill-in-a method what value to use when it comes across missing values in that column. And secondly, after a comma, we're going to enter another parameter. We're going to put in place, all one word, equals true with a capital T. And this just tells Python that we want to actually make that change on the sales data frame. So let's highlight that line of code and hit F9 to run, and let's go and open up our sales data frame. And we can now see that that 5th row contains our mean sales value. And this will also be the case for those other rows that we're missing. Again, this approach is not always the best way forward, but it does showcase the types of things that Pandas makes really easy for us. Right, so now we have fixed those missing values, let's move on to aggregating or summing all of our sales data from customer transaction level up to date level. To do this, we use another amazing piece of Pandas functionality called group by. So let's again start by creating an object, and let's call this sales_summary. Let's set that equal to our sales data frame dot group by and then parentheses. Within the parentheses, we want to specify the column that we want to group the data by. So in this case, that will be transaction date. Then after those parentheses in square brackets, we want to specify what it is we want to aggregate. So here, this will be, again in quotation marks, sales. Then at the end of those square brackets, we want to specify what aggregation function we want to apply. And this could be mean or count, but here we want to sum up the sales by date. So we are going to use dot sum and parentheses. Now at first, this can all seem a little bit confusing, but after you've done it a few times, it does become quite intuitive. And Pandas allows us much more complexity too, enabling us to aggregate up multiple columns at the same time and even apply different aggregations to each. But for now, let's keep things nice and simple. So if we run that line of code, we can see in the Variable Explorer that we have created our sales summary object. So let's open that up. All right, amazing. Look at this. We have a row for each day and then the summed up sales. Well done. You have essentially just created a simple but extremely useful sales report using Python. Now, one final thing. Let's make a really quick and dirty plot of this using nothing but pandas. Now in practice, you would probably lean towards Python libraries like matplotlib or Seaborn to do these visualizations, as they offer much more control over plot features and appearance. But all I want to do here is show you how easy it is to create something quickly. So let's put sales summary dot plot and parentheses, and then let's run that line of code. Now, if we head over on the right hand side to our plots tab, we can see that our plot has been rendered. And while it's not too much to look at, it gives us a lot of useful visual information about the sales trends through September. Seemingly, there are some daily fluctuations which you would expect. Some days, such as weekends, are going to drive more people into store, and even the weather can have an effect. Anyway, the one thing that's annoying me slightly about this is those date labels on the x-axis. They are all on top of each other and it's really taking away from the chart. So let's add one parameter in within the parentheses of our plot method, and that is ROT or rotation equals 45, and that's 45 degrees. So if we run this line of code again, we can see the updated plot, and I think that looks a lot better. Cool, so that is all we have time for here. We've imported some data from a CSV file into a Pandas data frame. We've dealt with some missing values and then aggregated the data up to create a simple sales report. And finally, we have created a really simple plot to show this all visually. This has been another whirlwind tour, but as I mentioned earlier, my aim here is just to show you that this is all within your grasp, rather than try to show you everything. This is really powerful stuff. Data scientists and analysts are doing these exact things every day, so it's really exciting that we have covered them here. I hope you've enjoyed it. I've had a blast running through it with you, and I will see you in the next video. Hello and welcome to this very exciting tutorial where we are going to be working on our first project. We are going to stitch together some of the knowledge that we've learned in the Intro to Python tutorial, and we're also going to see some new and interesting concepts that really show off what you can do within Python. Here we are going to very quickly extract a list of prime numbers below a certain set value, so potentially 20 or 100 or even, as you'll see and as promised, 1 million. Now, before we start, make sure that your working directory is pointed to your DSI mini course folder. And remember, you can do this by clicking the folder icon at the top right and selecting that directory. Once you've set that, save a new script into that folder by going to File, Save As, and name that script 003 Primes Finder. Now, very quickly, if you're not sure what a prime number is, it is just a number that can only be divided wholly by itself and 1. So 7 is a prime number, as no other numbers apart from 7 or 1 divide cleanly into it. 8, on the other hand, is not a prime number, as while 8 and 1 do divide into it, so do 2 and 4. Alright, let's get into this. First, let's start by setting up a variable called n, and let's set that equal to a value of 20. This value will act as the upper limit of numbers that we want to search through to find primes. So here, setting it to 20 means that we are essentially wanting to find all prime numbers that exist that are equal to or smaller than 20. We'll start with this to understand the logic and to test that it's working as we want, and then once we're happy, we will crank this right up to 1 million. Cool, so we want to start by creating a range of numbers that need checking. The smallest true prime number is 2, and as we've set n, our upper bound, to 20, this range of numbers will be every integer between 2 and 20. So let's call this object number range, and this is going to be equal to set and then parentheses. And I'll tell you why we're going to be using a set instead of something like a list in a minute. And then within those parentheses, let's specify range, as we want to create a range of integers between two numbers, and then another set of parentheses. And then within that second set of parentheses, let's set our lower bound, which will be 2, and our upper bound, which will be n plus 1. And the reason we use n plus 1 instead of just n is because the range logic that we're using here is not inclusive of the upper limit that we set. So if we set it to 20, our range of numbers would go from 2 to 19. There is a very good reason for this, but we won't get into that now. Let's also go back and discuss the fact that we're using a set here rather than a list or some other type of data structure. The reason for this is that sets have some special functionality that will allow us to eliminate non-primes during our search, and you'll see what I mean soon for this case specifically. Let's also now create a place where we can store any primes that we discover as we go, and let's just call this primes list. In this case, a list will be perfect for the task as we don't need any special functionality, just somewhere to store numbers. So let's put equals, and then to create an empty list which we can add to, we can just put in a pair of square brackets. Alright, let's run those 3 lines of code to create everything that we need. Now we are going to end up using something called a while loop to iterate or loop through our set of numbers and check for primes. But before constructing a loop, I always find it valuable to code up the logic and then iterate manually first. This means I can check that it is working correctly before I set it off to run through everything on its own. As we talked about in the Intro to Python tutorial, a loop is something that is really useful in programming. It allows us to repeat a set of instructions over and over again and potentially update some information as we go. We discussed that in Python there are 2 types of loops. The for loop, where we iterate through each element of some static pre-existing object. So for example, we could iterate through each word of a book and check for certain words, or we could iterate through a list of numbers and specify that when the number is even to undertake instruction A and when it's odd to undertake instruction B. The second type of loop that we discussed was the while loop, and this is where we don't necessarily iterate through a pre-existing set of data, but instead we iterate until some condition is met. We will be using a while loop here as we want to keep looping through our set of numbers, which will keep being updated until there are no more numbers to be checked. Anyway, like I said, let's construct the logic first and then put in place the loop later. So we have our set of numbers called number range to check through. And if we head over and have a look in the variable explorer, we can see that this contains all integers between 2 and 20. Let's extract the first number from that set as we want to check whether it is a prime number or not. If it is a prime, we're going to add it to our list called primes list. If it is not a prime, then we don't want to keep it, so it can be discarded. And we can just move on to checking the next number in our set. There is a special bit of functionality that we can apply that will remove an element and also provide that value to us, and that is called pop. So let's create a variable called prime, which will be equal to what the pop functionality removes from the number range set. So prime is going to be equal to number range dot pop and parentheses. And if we run that line of code there, we can see in the Variable Explorer that pop has extracted the first element from our number range. It's no longer included in the number range object, and it is now assigned to our prime object. Now, we actually know that the very first value in our number range is going to be a prime, as there is nothing smaller than it, so therefore nothing else could possibly divide evenly into it. As we know it's a prime, let's add it to our primes list object. And to do this, we'll use the append functionality that we learned about in the Intro to Python tutorial. So down on the next line, let's put primes list, the object that we're going to append to, dot append, and then parentheses. Within the parentheses, we want to specify what it is we want to append, and in this case, it's the value prime. If we run this line of code here and take a look in the Variable Explorer, we can see this value has indeed been added to our primes list object. And each time we discover a prime, we will add this value into the list, meaning that at the end of the whole process, we'll be able to see all of our prime numbers. Alright, so now we have done that, we're going to do a special trick to check the remaining integers in our number range object for non-primes, or essentially numbers which we now know are not primes. For the prime number that we just checked, in the first case this was the number 2, we want to generate all the multiples of that number up to our upper bound, which remember here we specified to be 20. We're going to again use a set rather than a list because it allows us some special functionality that we will use soon. And this is the magic of this whole approach. Right, so let's create this object which will hold these multiples, and let's just simply call that multiples. And that will be equal to set and parentheses, and within that set of parentheses, range and another set of parentheses. And it's worth noting that when we create a range, the full syntax is range, and then the starting point of our range, the stopping point of our range, and then we also have the option to include a step, which we can use if we don't want every sequential number. So if we wanted the numbers in our range to increment like 2, 4, 6, 8, we could put a step value of 2. So for our range here, for the starting point, we don't need our number, as that's already been added as a prime. We can instead start our range of multiples at 2 multiplied by our number, as that will be the first multiple. In our case, the prime we just discovered is 2, so the first multiple will be 4. If the number we were checking was 3, then the first multiple would be 6, and so on. So for our starting point, let's just put our prime number multiplied by 2. For the stopping point of our range, we specify that we want our range to go up to 20. So again, we will use n plus 1 to specify that we want 20 to be included. Now the step is key here. We want multiples of our prime number. So we want to increment in steps of our number. So we can put in our prime variable here, which means it will always increment by the right amount. If we now run this line of code, we can see in the Variable Explorer that it has created this multiples object, and it does indeed contain all multiples of 2 up to 20. The next part is the magic I spoke about earlier. We are going to use some functionality that can only be used on a set, and this is called difference update. What this does is it checks the values of one set against the values of another set, and it removes any values from the first that also exist in the second. Here, we want to remove any values from our number range object that are multiples of the prime number that we just discovered. The reason we're doing this is because if a number is a multiple of anything other than 1 or itself, then by definition it is not a prime number and can safely be removed from the list to be checked. So before we apply the difference update functionality, let's take a quick look at our two sets in the Variable Explorer. Our number range set currently has all integers between 3 and 20. And our multiples set has the values 4, 6, 8, 10, 12, 14, 16, 18, 20. Difference update will update our number range set to only include the values that are different from those in the multiples set. So back to our code. To do this, we will put in our initial set or the number range object and then apply the difference update functionality with our multiples object. So let's do this together. Number range dot difference update, and then in parentheses, let's specify multiples. Cool, so let's run this line of code. Now, when we look at our number range object up in the variable explorer, all values that were also present in the multiples set have been removed, as we know they were not primes. And let's stop and think about this for a second. This is quite amazing. We've just made a massive reduction to the pool of numbers that need to be tested as primes. So from a processing point of view, this is super efficient. It also means that the smallest number that remains in our number range object is a prime number, as we know nothing smaller than it divides into it. And this means we can run all of our logic again from the top. So let's again run this first line here to remove the smallest number from our number range and pop it into the prime object. So let's run that, and we can see that number was 3 and it has been removed from the number range object. As we discussed, since we know this number is a prime, we can append it to our primes list. So let's run this second line here to do just that. So let's run that line and we will see that it has been added to our primes list. Next, we're going to overwrite our multiples object with multiples of 3 up to our upper bound of 20. So let's run this line of code here, and in the variable explorer you can see that the multiples object now contains the values 6, 9, 12, 15, 18, all the multiples of 3 from 3 up to our upper bound of 20. And exactly the same as last time, if any of those multiples exist in our number range object, we remove them using difference update. So let's run this fourth line of code here, and we can see that again we've whittled down our number range object, and we can see that the smallest remaining number is now 5, which is also a prime. Now we could keep manually running these 4 lines of code until our number range set is exhausted, but we know that there is a clever solution to this, and we spoke about it earlier, the while loop. So between these 3 lines of code here where we set everything up and our 4 lines of logic here, let's put in place one of these while loops. To do this, let's just enter down one space, and then we are going to put while number range and then colon. And this will tell Python that the loop should keep running until that number range object is empty. There are a few different ways to run while loops based on the conditions that you want, and you'll learn about those as you delve into Python further. This approach here, however, works perfectly in our case, as we want to keep checking for primes in our number range object until no more can be checked. After that, we need to indent our 4 lines of code, as this tells Python that we want all of those lines to be part of this while loop. We briefly discussed this in the Intro to Python tutorial, and this indentation is a fundamental part of how a lot of logic within Python works, and the more you use it, you will start to see how common this is. To do this, we can just select all 4 lines of code here and hit Tab. Perfect. Now, after this loop logic, let's print out the primes list to the console to have a look at what we find. And just to be clear, when we run all of our code, Python runs things in sequential order. So the loop will go about all of its business before Python moves on to any more code. So after it's run, we should have our full list of primes, and we can access and analyze them at this point. So to print out our list of discovered primes, let's put in the print statement, and we'll put that up against the margin again, as we're not wanting this to be part of the loop. And then within parentheses, let's just pass in our primes list object. Next, let's get some interesting stats from our list of primes. Firstly, the number of primes that were discovered. Let's call this prime count, and let's set that equal to len, which means length, and then parentheses. And within those parentheses, we will again pass in our primes list object. This will simply count up the number of elements in our list. Let's also find out the largest prime number that we discover. So let's call this largest prime. And this time, let's set that equal to max and parentheses and primes list again. Finally, let's print out all of this information using something called an F string, which means that we can print out text but dynamically include data from variables or objects that we have created. So to do this, we put print and then parentheses, and then we are going to put the letter F and then quotation marks. Then within those quotation marks, we will put there are, and then space, and then curly braces. And within this set of curly braces, we're going to put in the prime count variable. Then after that set of curly braces, let's put prime numbers between 2 and then another set of curly braces. And here we're going to put in n, which is our object denoting the upper bound for which we're searching for primes beneath. Then after that set of curly braces, let's put comma and let's put the largest of which is, and curly braces again. And this time we're going to put largest prime. Perfect. So head to the end of that line and enter down, and we are good to go. So let's highlight all of our code and hit F9. Amazing. So down in the console, we can see that everything has run fine. We can see the list of primes has been printed, and that looks pretty good to me. And then we can see at the bottom our dynamic string has been printed too, and it says there are 8 prime numbers between 2 and 20, the largest of which is 19. Nice work. So now we know our logic is working. Let's crank this up a little bit. So at the very top, instead of n equals 20, let's just change that to 100. Let's again just highlight all of our code and hit F9. Cool, so there are 25 prime numbers between 2 and 100, the largest of which is 97. Now, I did promise you 1 million, so let's do that. Let's change the value from n to be 1 million, so 6 zeros after the 1. Now, before we highlight this and run it, let's make one quick change. Let's go down here to where we print out the primes list and comment that line of code out. So all we need to do is put the hash symbol at the front, and that line of code will not be run. I'm sure we're going to discover a lot of prime numbers here, and we probably don't want to print them all to the console. Anyway, let's now highlight all of our code again, and now the moment of truth. F9. Wow. There are 78,498 prime numbers between 2 and 1 million, the largest of which is 999,983. That was fast. It started with a set of numbers to check that contained every integer between 2 and 1 million. In about half a second, it whittled that down to 78,498 prime numbers. How cool is that? Anyway, that is it for this mini project. I've had so much fun running through this with you. I hope you enjoyed it. I know that we covered some new and potentially strange concepts at breakneck speed, but I really just wanted you to build something amazing, as instead of teaching all the fundamentals here, I want to try and pique your interest and show you what can be done. And then if you're interested in learning more about while loops, or why we used a set instead of a list here, or what other functionality can be applied in a similar way to difference update, then you can go back and explore it as you learn more. But I really wanted you to get excited about Python first. So go and show your family and friends your amazing Primes Finder code. I am sure they will be blown away with how quickly it runs. Well done for getting through this. You should genuinely be really proud of what you have built here. And I will see you in the next tutorial. Hello everyone, and welcome to this tutorial all about machine learning. Here I will be introducing this exciting, interesting, and cutting-edge field at a very high level in a way that will help you understand where it fits into the bigger data picture, why you might use it, and also some of the broader applications where it is being put into place. Now, the obvious question for anyone who is getting into machine learning is, what is it? and there is not one accepted definition in the field, and this is partly due to the somewhat overlapping remits of some other key terms that are used in the industry, namely artificial intelligence, deep learning, and even data science itself. We'll get to those very soon, but first let's try to put a definition on machine learning so we can compare it against the others. In my view, the best definition of machine learning is algorithms that learn from data and then apply those learnings to make informed decisions and/or predictions on new data. So understandably, this is a very high-level definition, but this captures two essential parts of a lot of what machine learning is all about. There is a part where some form of learning takes place, and this is where algorithms will learn relationships or patterns within our data. There is also a second part, which is the application of these learnings, and primarily this will be to make predictions for new data or for the future. So we've got a bit of a definition now, but how does this compare to those other terms that I just mentioned? Well, I think this chart best represents those relationships. AI, or artificial intelligence, is actually the broadest term, with machine learning being a subset of algorithms within it. Deep learning is actually a more niche subset of algorithms within machine learning, specifically those using neural networks. And then data science is a somewhat lateral term that is becoming broader and broader all the time, covering mathematics, computer science, analysis of data, and AI. There will never really be agreement on these terms and the specific boundaries that they cover, but it is good to have an understanding of how they do relate to each other. So now we've learned about where machine learning fits into the bigger picture, I guess the next question is, why do we need it? Well, let's for a minute imagine that we are head of marketing at an online movie and TV streaming company, a competitor to the likes of Netflix, Disney Plus, and Prime Video. We have several new movies coming out next month. We have this action movie with the kick-ass female lead. We have this horror movie about empty park benches apparently, and we have this kids movie about a child magician. We want to email all of our customers to tell them about the new releases, but the problem is we only have one image slot in our email template, so we need to know which customers should have which movie featured in their email in order to maximize the chances of getting them to stream our content rather than leaning towards Netflix or some time gaming on their PlayStation. One approach to this problem would be to attack it manually. As head of marketing, we could come up with some rules about who should get what. We could analyze all of our data and try to rank every customer based on what we believe to be their preferences. And while this is possible, it's likely going to take a very long time. I mean, we would have huge volumes of data to comb through. And what about next month? We'll have 3 new movies from different genres, and we'll have to come up with completely new rules. This is where machine learning comes in. We can essentially set it loose on our data and get clever algorithms to figure out the patterns that exist within. Perhaps we would want a percentage likelihood that a customer would watch each of these movies, or perhaps we want to segment up our customers based on their historical viewing habits. We can do both and much, much more. The algorithms we use won't ever base decisions on pre-held beliefs or opinions. It'll only ever learn what is represented within the data. These are really powerful concepts, and I hope you're as excited as I am, because the possibilities are almost endless. Right, let's slow down for a second and get a little bit more philosophical and discuss whether machines really do learn. When we refer to machine learning, it's often argued that machines don't really learn in the same way that a human or animal does. To simplify, machine learning is really about finding relationships in data and then generalizing these findings into some rule that can be applied to new data, on the assumption that the new data is similar enough to the data on which that rule was created. In my view, humans do actually learn in the very same way. We take all of our experiences and then apply our learnings to new scenarios every day. It's just that our brains are so broad and so complex that the input data is so diverse that it's hard to compare the two. I personally don't think what we do and what machines do is that different. Humans have the distinct advantage of depth. The sensory information we take in for any scenario is far richer than any data set that currently exists. The one example that always confirms this for me is when we're walking down the street and we smell something. and it takes us back to some moment in our childhood. Our brains are so incredibly rich and deep that from nowhere we pull out a memory that we've not had at the front of our mind for years, based only on some brief aroma. Machines, on the other hand, while not currently able to work with the richness of data that the brain does, do have one distinct advantage: speed. Computers can run through data at an exceptional rate. Take a machine learning model that's being given information about the game of chess. It could potentially run through thousands of completed games per second, something we as humans just cannot do. So while the context for learning is slightly different and both humans and machines have different strengths, in my view, the overall process isn't too dissimilar. And since we're talking about learning here, this is a good time to mention that machine learning is commonly divided up into several types of learning, with the two most prominent being supervised learning and unsupervised learning. Supervised learning is where we have both inputs and outputs, or what are often known as labels, and we ask the machine to learn a mapping or some set of rules between the two. This means that when we get new, unlabeled data like the triangle at the bottom of the screen, we can apply this mapping or this set of rules and get a prediction for the output. Here I've represented the inputs as shapes and the outputs as the name or the type of each shape. But in reality, our inputs might be features of a house, for example. So the age of the house, the size in square feet, the number of bedrooms, and the neighborhood that it's in. And the output might be the price or the value of that house. We could build a model which will look to learn the relationship between those features and the price, and then predict the value of any other house based on its features. And these types of house price prediction models do actually exist and are commonly used in real estate to help you assess the value of your house or a house that you might be interested in. One other important thing to know about supervised learning is that there can be two types of outputs that we might want to predict, and these define the two types of problems or tasks that are solved in this area. Firstly, there is regression, and regression is where the output or the label is a numerical value, examples of which would be dollar values such as sales or speeds or distances. Essentially anything where the output for each data point is a single numerical value. Here, we're asking the model to predict these values as accurately as possible. When we code up our model later in this mini course, it will be a regression problem that we're tackling. We're going to be looking to predict how long in seconds it will take video game players to complete a particular challenge in their game based on their level and the amount of ammo their character has. So that is going to be super exciting. But let's keep putting in the groundwork before we get there. The other type of task within supervised learning is classification. And as you can probably guess from the name, this is all about predicting which group or which class a data point will be in. Examples could be a simple yes or no, perhaps predicting whether a customer will sign up or if a customer will churn, predicting whether an email is spam or not, and we can even predict into multiple groups, so perhaps predicting images of animals as either dogs, cats, rabbits, or horses. So this idea of regression and classification is a really important distinction within supervised learning, and we'll often use different algorithms to solve these two types of problems as they are fundamentally different tasks. Right, so that is a little bit about supervised learning. Let's now take a look at unsupervised learning. And here we find ourselves in a different situation. In supervised learning, we just saw how we had both input data and output data or labels. Well, in unsupervised learning, the data is essentially unlabeled. And what I mean by that is we really just have input data. We don't have some other output variable that we're looking to predict or to classify. Instead, the goal in unsupervised learning is to find structure and patterns within our data. There are a number of different tasks that sit within unsupervised learning, but a very common one is called clustering. Clustering is where an algorithm looks to separate all of our data points according to how similar or dissimilar they are to each other, ending up with distinct groups of data points or what are known as clusters. But why might we want to do this? We have the data, we can look at it any way we want. Why would we want to dynamically group it up? Well, a good example of this in the real world would be the supermarket customers we see here. A clustering algorithm could take in data around all of their shopping behaviors, things like the types of products they purchased, how often they're coming into store, and perhaps even the time of day that they most often shop. And the algorithm would create a number of clusters, each of which would denote a distinct shopper type that the supermarket can then track over time and target specific marketing strategies towards, as they know all customers in each cluster are similar to each other but different from those in the other clusters. It's quite a simple concept, but it is one of my favorites, and it has very powerful applications within business and is often utilized in customer segmentation projects. Another common task within the world of unsupervised learning is known as association rule learning. You might not know that you know about this, but you definitely do. Imagine a situation where you have purchased a product online. Let's say some shiny new golf clubs like we see here. Now, what do you always see as you are nearing the online checkout? You see something like this. This is an example of cross-sell marketing, where companies can infer based on a lot of historical customer behavior that if you buy product A, then you're likely to also buy product B or product C, and thus can recommend you these products to tempt you to part way with a little bit more of your cash. Now, while we've been discussing supervised and unsupervised learning so far, there are actually two other types of learning that are commonly spoken about in machine learning, those being semi-supervised learning and reinforcement learning. While we could discuss these here as well, I've made the conscious decision to exclude them, as in a commercial or business setting, these are quite uncommon, at least when compared to supervised and unsupervised techniques. I want to ensure that we are really focused on getting a solid understanding of those without spreading ourselves too thin, although I think it's useful to know these names. So in saying all of this, let's now take a look at where machine learning is actually being applied. In today's world, virtually every industry has machine learning applications being built and implemented. You'll know the big ones, I'm sure. Alexa and Siri are answering your questions. Tesla is building self-driving cars. YouTube, Facebook, and Netflix are recommending you relevant content. You may have also heard that DeepMind, a Google company, built AlphaGo and subsequently AlphaGo Zero and Mu Zero, programs that learned to play the board game Go and in the space of a few weeks reached a level of ability that surpassed thousands of years of human play. Now, this is no mean feat, considering Go has more possible board states than there are atoms in the universe. But perhaps it is the lesser known applications that you might find more interesting. Image recognition tools are now outperforming teams of doctors at recognizing abnormalities in tissue samples. Police forces around the world are looking to implement facial recognition tools. Systems are being implemented on farms to analyze weather conditions, temperature, water usage, and soil conditions. Your bank is predicting your cash flow, your mobile phone company is predicting the likelihood that you'll leave them, and Facebook can work out very accurately who you will vote for in the next election. Clothing stores are developing changing rooms that can tell you what is in stock and make personalized recommendations. Fast food chains are dynamically changing drive-through menus based on the time of day, weather, traffic, and your order, all in an attempt to get you to spend a little more. Machine learning is being used to predict the next musical or cinema hit, judge beauty contests, create the perfect perfume just for you, and even spot sharks and crocodiles in Australian waters. So as you can hopefully see, machine learning really is everywhere. So there is no doubt that it is something important to learn about and to understand, and I am extremely excited that together we are going to go one step further and actually code up one of these algorithms ourselves. So let's not spend any more time here. Let's discuss a little bit about scikit-learn, the machine learning library that we will be utilizing within Python, and that is exactly what we will cover in the next video, so I will see you there. Hello and welcome to this tutorial where we will be learning all about scikit-learn, what it is, what it covers, and some example code to ensure that you hit the ground running when we get into our practical tutorial. So let's dive in. Scikit-learn is a machine learning library for Python, containing algorithms for supervised and unsupervised learning, as well as data pre-processing techniques. It uses a really consistent code structure across all model and algorithm types, not only making it really easy to learn, but enabling you, the user, to quickly test different algorithms and find the one that will best solve your problem. So, what can we do in scikit-learn? Here I've created a bit of a map showing what scikit-learn contains. There are algorithms designed for supervised learning tasks, and this includes those suited for regression problems, algorithms such as linear regression, regression trees, and random forests, which is what we will be building very soon, as well as many others. Algorithms for classification problems are covered, including the common ones like logistic regression, classification trees, and random forests again, as well as many other algorithms for these tasks too. For unsupervised learning problems, we've got clustering algorithms such as k-means and hierarchical clustering, as well as algorithms suited for dimensionality reduction like PCA or principal component analysis. Now, it's not just models and algorithms either. All the useful tools you will need are covered, including those for data pre-processing and preparation. Things such as feature selection, where you can learn which input variables are most important in cases where you have a lot of them. Feature scaling, to ensure all input variables are on a similar scale, which can be vital when dealing with distance-based algorithms, as well as logic for things like one-hot encoding, which helps turn categorical or text-based variables into a numeric form which the model can more easily understand. There are also some very clever techniques which I've labeled model refinement, things such as logic to split your data into training and test sets to ensure that we can robustly understand the performance of our model, parameter tuning to ensure your model is using the optimal settings, and even model selection techniques, which are ways to assess which type of model is best suited for your particular problem. All in all, it's an extremely useful library to be familiar with if you are looking to build and apply machine learning models in Python. So now we've discussed what it contains, I want to run through some very simple sample code so you can see what it might look like when we get to the practical tutorial. So here is the bare bones of training and validating a model using scikit-learn. This code here is using a linear regression model rather than a random forest like we will be putting into place. But to be honest, the structure is virtually identical. And this is actually one of the amazing things about scikit-learn. You can change the type of model you're building with very little changes to the actual code. Now, all of this may look a little bit scary to start with, but I will run through each chunk of code and explain at a high level what it is doing. The purpose of this is to get you familiar with the types of things that you will see in the practical tutorial and will mean you will hit the ground running. Firstly, once in Python, we will be importing a model type and other tools from scikit-learn, and you'll notice that this is referred to as sklearn here rather than the fully spelled out scikit-learn. In our example code here, you'll see in the top line of code that we are importing linear regression. If we were running a different type of model, we'd import that instead. And we will be using the random forest regressor when we get to the practical tutorial very soon. Under that, on the second line, you can see that we are also importing some functionality to split out our training and test sets. It is best practice to train your model on one set of data and then validate or test its accuracy on another dataset, one that the model never got to see. These models are very sneaky and they can try to learn the absolute specifics of a dataset, and while this seems good at first, it can mean that it learns the rules so well that it actually struggles when given new data, as there might be some things that it hasn't seen there. Assessing the accuracy on an unseen set of data means that we're taking this into account. On the third line, we're importing some logic that will help us calculate R², which is a key metric for assessing the accuracy of the predictions on a regression task. Next, I've basically put in some placeholder code for where we might import our raw data. As this is a very simple example here, I'm just suggesting that our data is sitting in a CSV file and that it doesn't need any special pre-processing, it's just ready to go as is. In reality, there is often some cleaning and preparation that does need to happen, but let's not worry about that now, as this tutorial is more about understanding the logic involved in a scikit-learn pipeline rather than every possible path that you could go down when building a model. Next, as our example is showcasing a supervised learning problem, we would have both inputs and a known output. In scikit-learn, we need to split our data into two separate objects. The common way to do this is to create an object called uppercase X, which holds our input variables, and then an object called lowercase y, which contains our output variable, or what is sometimes called our target variable or dependent variable. Whatever you refer to it as, this is the variable that we are looking to predict. Next, we split out our X and Y objects into some training and test sets, and we do this utilizing the train test split functionality that we imported from scikit-learn at the top of our code. The way we use this is to list out 4 objects separated by commas, as these are the 4 outputs of the train test split function. Within the parentheses of this function, we feed in our X and Y objects and we specify the ratio for this split. Here we've specified that we want 20% of the data to go into the test set, with the remaining 80% to go into the training set. Now we're at a stage where we've completed our setup, so let's get into the modeling steps. Here we set up the shell of our model as an object, and as we're applying a linear regression model in this code example, we specify the linear regression class that we imported at the top. Within the parentheses here, we could specify any parameters that we want to apply for this particular model. Leaving it blank means the default settings will apply. For regression models, a common approach is to call this object regressor, but you can call it anything you like. Now we have our model in the form of a regressor object, we can train it using the fit method. You'll notice that we're feeding in the xtrain and ytrain objects, which are the inputs and output for our training data only. This is pretty amazing when you think about it. Training the model is the biggest part of this whole process, and it all takes place within this short line of code. And this illustrates the beauty of scikit-learn. It really makes machine learning clean and easy. So once we have run this line of code, our model will be trained. Once that's done, we really need to understand if it's any good at predicting the output. In other words, did it find any predictive power in those input variables that could accurately predict the output? Our regressor object has a predict method, which will apply the rules of the model to any new data. Here we apply this predict method to the xTest object, which contains only the input variables of the test set. The result of this is that we get predicted output values, and in this case we're saving these predictions to an object called y_pred. Now we have predictions for the test set, we can compare these to the actual output values for the test set and evaluate the accuracy of our model. Just to be super clear, we have used the model to predict the output variables for the test set, and we're then comparing those to the actual output values. In the code example here, we are calculating the R² metric using the functionality that we imported at the top of the code. This will give us a value between 0 and 1 that tells us how accurately our model is predicting the values for the test set. So I know that was a whirlwind tour of the code, but we will cover it all again when we code this up. I think it is useful to get the cogs ticking over now, however, so we hit the ground running when we're in Python very soon. Overall, I hope you're starting to see why scikit-learn is such a useful library for machine learning, and I really hope you see that even though there is a lot of complexity involved, the code itself isn't that scary. In the next tutorial, we will be learning the theory behind a random forest model, and then we'll be straight into Python to get our hands dirty and code this all up. I will see you there. Hello and welcome to this tutorial on the theory behind a random forest model, which is what we are going to be building together in Python in the next tutorial. I'm going to start by saying that random forests are genuinely my favorite type of machine learning model. They are one of the most commonly used and powerful machine learning approaches. They frequently provide very good prediction accuracy and are renowned for their robustness, meaning they need very little technical tuning and tweaking to work well. Now, I'm not expecting you to know anything about this type of model, so let's dive in and start by discussing what exactly a random forest is. A random forest is an ensemble model consisting of many decision trees working together across different randomly selected subsets of the data, facilitating improved accuracy and stability. At this point, you may have, several questions. one of which might be, what the heck is an ensemble model? Well, an ensemble model is simply a model that is comprised of a number of other models, and it takes the predictions from each of those models to form an overall prediction.
Wait, so an ensemble model is simply a model that is comprised of a number of other models and it takes the predictions from each of those models to form an overall prediction.
All right, you would be forgiven to be somewhat confused still. That sentence was bordering on something from Dr. Seuss's Fox and Socks. Let's think about this in a better way. A good analogy for a random forest is to think of a competition where you and your colleagues or friends have to guess the number of jelly beans in a jar. Your guess is most likely going to be too high or too low, and in reality, so are the guesses of all of your jelly bean guessing rivals. However, if you were to average all of the guesses, it's likely that you're going to end up with a number pretty close to the correct amount. The idea of ensemble models is specifically this. Putting together a number of weaker models will provide one stronger model. And I think that is pretty cool. Now, back to our definition. In the case of a random forest, we are talking about a number of decision trees all working together. So let's quickly understand what a decision tree is. A decision tree is a model that splits the data into distinct buckets using the input variables, with split decisions being based on how well each potential split explains differences in the output variable that we are looking to predict. It's called a decision tree because it eventually starts to resemble an upside down tree, with branches representing each split and leaves or leaf nodes representing the final buckets of data. You'll also equate the final look of it with a flowchart, but let's actually take a look at one. I know it will make a lot more sense once you see it in action. So let's imagine a scenario where a girl called Lucy runs a lemonade stand. Each day she records the number of lemons that she uses, the daily peak temperature, and whether it rained or not that day. She wants to build a model to predict the number of lemons used on any given day, and she wants to do this using the input variables of temperature and rain. So with a decision tree, we start with no splits at all, or in other words, with all of our data. And we can calculate that across all days in our data, the average number of lemons used is 100. What the decision tree will do from there is to test all the possible ways it can split each input variable, and for each one of these potential split points, it will assess how much difference there is in the output variable, and it will select the split with the biggest difference. In the case of Lucy's lemonade stand, it wasn't whether it was raining or not. The biggest difference in the number of lemons used was a split in the daily peak temperature, and more specifically, a split at temperatures on either side of 20 degrees Celsius. The algorithm found that on days where the temperature was above 20 degrees, the number of lemons used was significantly higher than those days where the peak temperature was less than or equal to 20 degrees. The difference at this particular split point was more apparent than at any other point, so it selected this as the first split in the tree. What happens next is interesting. The algorithm then goes into each of those newly formed buckets and repeats this process, checking and assessing all possible split points that remain, and using the one with the largest difference in lemons used as the split to make. So in the case of the bucket on the left, the algorithm then went on to select the split between whether it rained or not, and we can see that this split out the number of lemons used even further. The same checks and tests were run on the other side of the tree, and there we see that it split again based on temperature, this time at 10 degrees. So if this was the final state of our decision tree, then we would have 4 leaf nodes, which I've labeled here as A, B, C, and D. Leaf node A is for days where the daily peak temperature is over 20 degrees Celsius and it is not raining. On those days, we expect around 169 lemons to be used. Leaf node B is for days where the daily peak temperature is also over 20 degrees and it is raining. On those days, we expect around 111 lemons to be used. Leaf node C is for days where the daily peak temperature is greater than 10 degrees but less than or equal to 20 degrees. On those days, we expect around 89 lemons to be used. Leaf node D is for days where the daily peak temperature is less than or equal to 10 degrees. And on those days, we only expect to use around 45 lemons. So if we were to use this decision tree model, what what happens when we need to predict the number of lemons for tomorrow? Well, it's actually quite simple. We would just follow the decision tree path with the information that we have. So if the forecast for tomorrow was for rain with a peak temperature of 27 degrees, then we would follow the rules and find the appropriate leaf node. So the forecast of 27 degrees means that we fall into that left node, which represents anything over 20 degrees. And from there, we'd follow the next split into the node that represents days where it is raining. Our prediction is gained from that leaf node and would be that we will need 111 lemons. Alright, so now we know a little bit about decision trees. Let's head back to the world of random forests, which we learn are an ensemble of decision trees all working together. And here I've visualized 6, but in practice this could be tens, hundreds, or even thousands of trees. And before, where our single decision tree provided a single output prediction for some combination of input variables, and in this arbitrary illustration here, this decision tree at the top left provided a prediction of, say, 7. In the case of a random forest, each of the decision trees will provide a prediction. We can then take the average of all of these predictions and use this as our final prediction. It all kind of makes sense, right? But you may well be asking, why is the prediction for each decision tree different? Surely they should give the same prediction. Well, the answer to that lies in the name. We're using a random forest. So let me very quickly mention what is random about each of the decision trees. Firstly, each decision tree is built using a random sample of our data. And each time a split decision needs to be made in the decision tree, it is only offered a random sample of the input variables to choose from. Now, we're not going to go into the depths of how this algorithm does this, as I really want to keep pushing forward in our whirlwind overview, but it is worth emphasizing again that this randomness for each of the trees in the forest is exactly what we discussed in the jelly bean example. Each tree is slightly handicapped, but in a different way, and therefore each has a slightly different view of the world. When we average all of these predictions from these weaker models, we end up getting really robust and accurate results. So with all of this in mind, let's get into Python and code one of these models up. I am really excited for this, so I will see you there. Hello and welcome to this practical tutorial where together we will be coding up what is required to train and test a random forest model using the Python library scikit-learn. As we learned in the Introduction to Scikit-learn tutorial, and as you'll see here, scikit-learn makes this process super clean and easy for us. Like we've done in the other practical tutorials, we are going to move through this reasonably quickly, and we won't be diving into the depths of everything that we do. As I've said before, what I really want for you in this mini course is to see what you can achieve by building out some really interesting projects. And if you want to know more, and trust me, there is a lifetime worth of more that you can learn, then I urge you to do so, and I am more than happy to support you on that journey. Anyway, without further ado, let's get cracking. Right, so before we start, make sure that your working directory is pointed to your DSI mini course folder, which you can do with the folder icon at the top right. Once you've done that, save a new script into that folder called 004 Random Forest. You'll see that I've got some headings in my code here to make it nice and easy to follow, so feel free to add those into your code as we go. Perfect, now let's get straight into this and import all of the Python packages that we require. We will essentially follow the code template that we ran through in the Introduction to Scikit-learn tutorial, but of course, since we are building a random forest here rather than a linear regression model, there will be some very subtle changes. Since we are building a random forest model for a regression problem, in other words, the values we are predicting are numeric, we will import the random forest regressor class from scikit-learn. And to do this, we put from sklearn.ensemble import random forest regressor. So no spaces and with capital letters for each word. Then, down on the next line, let's import the functionality that we need for a simple test-train split, where we split out all of our data into a training set for which we will get the model to learn the rules and relationships between the input variables and our output variable, and then a test set which the model will not see in the training phase, meaning that we can get a good understanding of how well those rules work when applied to new data. Scikit-learn has all of this covered for us, so from sklearn.model_selection import train_test_split. We also want to understand how good our predictions for the test set are when compared to the actual values. In a regression problem, it is common to use something called the R-squared metric, and again, scikit-learn has some inbuilt functionality for this. So, from sklearn.metrics import R_score. Let's also import pandas as PD so we can bring in our data. And on that note, you will need to have downloaded the video game data CSV file based on the instructions prior to this tutorial. And you will want to have put that CSV file into your DSI mini course folder. If you've not done this, please do so now as we will need it. Right, so to import our CSV file, we will use pandas. So let's call our data frame my_df, and let's set that equal to pandas, so pd.read_csv and parentheses. Within the parentheses, as our video game data CSV file is in our working directory, all we need to do is put quotation marks and name that file. So video_game_data.csv. Let's run that line of code there to bring in our data, and let's not forget to run our import statements as well. So let's run all of that, and then let's head over to our variable explorer. And there we can see our my_df data frame exists, so let's double click on that to open it up. Right, so really simple. We have 30 players in total who have already completed this level in the game, and we have two input variables. Firstly, we have their current level in the game at the point that they started this challenge, and we have the amount of ammo that their character had at this point as well. Then we have our output variable that we are looking to predict, which is their completion time for this challenge in seconds. Cool, so now we're happy with our data. Let's head back to the code. Now, the aim of this approach is to understand relationships between input variables and the output variable. Scikit-learn requires us to separate out the inputs from the output and have them stored as two separate objects. It's a common approach to label these objects uppercase X and lowercase y, and you'll see this again and again the more you use scikit-learn, as virtually every model that you'll build will work in this same way. So for our X object, which will contain our input variables, so level and ammo, we're just going to take a shortcut and just drop the completion time column instead. So let's put x equals my_df dot drop and parentheses. Within the parentheses, we're going to put a set of square brackets and then specify the column that we want to drop. So this here will be completion_time. Then after those square brackets, let's put a comma, and then we're going to put axis equals 1. And this just tells Pandas that we're wanting to drop a column rather than a row, as the drop functionality that we are using can be used for both. Now down onto the next line, for our y object, let's just keep completion time, and this is quite easy to do. So y equals my_df again, and then square brackets, and again we're just going to put in completion time. Cool, so let's run these two lines of code to create those objects. Now, as I mentioned earlier, we want a way to reliably assess how good our model's predictions are. Building a model in a way where we can trust in its predictive abilities on new data is extremely important. A model that works well only on the training data but not on new data is almost worthless. We need to be able to rely on the model and understand what it will do when put into production. At a high level, model validation should be done in a way where we split all of our data into two groups, a training set that we use to train the model with, and a test or validation set which we use to get a true understanding of how accurate the predictions are on new or unseen data. Assessing model accuracy on the same data that the model was trained with is problematic, as the model can do something called overfit, where it learns the patterns of this data so precisely that when given some new data in the real world, it finds that those rules don't really apply very well. So in saying all of this, let's now split our X and Y objects into training and test versions. To do this, we will use the train test split functionality that we imported at the top of our code. And this has 4 outputs, so follow along with me here. Let's put x underscore train and then a comma, and let's put x underscore test. After another comma, let's put y underscore train and another comma and y underscore test, and then equals. Now let's copy down the train test split functionality here and paste that in, followed by parentheses. Within the parentheses, we are going to pass the x object and then the y object. After another comma, we're going to specify how much data we want to go into the test set. And we do that using a parameter called test underscore size. And here, let's set that equal to 0.2, which will mean that 20% of our data will go into the test set and the other 80% will be used for training our model. There is one more parameter that we are going to put in, so let's put in another comma and let's put random underscore state equals 42. And random state is just a parameter that can ensure that you and I will get the same splits in this data. And therefore, if we both use random state equals 42, then therefore we should get the same results as we run through the rest of the code. So let's head to the end of that line of code, highlight it, and F9 to run it. And we can see in the Variable Explorer that those 4 new objects have been created. And we can see that our training data has 24 of the 30 data points and our test data has the remaining 6. So we will train our model on 24 of our players and then assess the predictions on the other 6. Of course, in the real world, you'll be using much more data than this, but I think it's quite important early on to be able to see everything in action, and that's why we're using quite a small volume here. Alright, so now our data is ready to go, we want to instantiate or simply create our random forest model object. And a common convention when creating regression models is to call this object regressor. Then all we need to do is set that equal to our random forest regressor object. So let's paste that in, and then afterwards we're going to put parentheses. Within the parentheses, we will just put in one parameter here. There are lots of ways that you can tweak and tune our model, but for now we are just going to put in random state equals 42 again. And this will again mean that you and I get the same results when we run our models. So let's head to the end of that line, highlight it, and again run it using F9. And just like that, our model has been instantiated. And now our model is instantiated, we can pass it our training data and get it to learn the rules that best map the inputs to the output. To do this, we type regressor, our model object that we just instantiated, dot fit and parentheses. Within this set of parentheses, we're going to pass it both the inputs and the outputs for our training data only. So x underscore train, comma, y underscore train. So let's run that line of code, and just like that, our model has been trained. And this is pretty mind-blowing when you think about it. Scikit-learn makes things so clean and easy that in this very simple and short line of code, we have trained our random forest model. Very, very cool. And now the model has been trained based on our training data, we can now test how well it performs on our test data, which we held back. Here we want to pass the input variables, so level and ammo, for our test set to our model. We'll save these prediction values so we can compare them to the actual values and get a feel for how accurate our model's predictions are. So let's create an object called y underscore pred. And that will be equal to, again, our regressor object, but this time dot predict and parentheses. And then within here, we are going to pass it x underscore test, which, like I said, is the input variables for our test set. So let's run that line of code there and create those predictions. And if we go over to the Variable Explorer and open up our ypred object that we just created, we can see the predicted completion times for those 6 players. But what we really want to know is how well we did. How do these predictions compare to the players' actual completion times? And we have that data. It's just our yTest object, which are the output values or the actual values for our test set. So let's put those 2 pieces of data together into a Pandas data frame so we can make this comparison. Let's call this prediction_comparison, and we will create a new Pandas data frame. So let's put equals and then pd.dataframe with a capital D and capital F and then parentheses. Within the parentheses, let's put in a set of curly braces, and within there we will specify our first column name. So within quotation marks we will put actual. After that, let's put a colon, and then let's specify the data that we want to fill that column, and this will come from our y_test object. After that, let's put a comma and enter down and create our second column, this time called prediction. After that, again, we will put a colon, and the values for this column will come from our y_pred object. So let's run all of this here to create that data frame. Perfect, and let's go over to the Variable Explorer and open that up. Right, so overall, I think we've done pretty well. Looking at these 6 players here, this first player had an actual completion time of 104 seconds, and we predicted 124 seconds. The second player had quite a slow time of 141 seconds, and we predicted 125 seconds. These 2 players were a bit faster, 88 seconds and 74 seconds, and we predicted pretty accurately there, 86 seconds and 93 seconds. This player did it in 120 seconds, and we were really accurate there, 122, 123 seconds, and then another accurate prediction here. So looking at this, when a player was actually slower, our models predicted a slower time, and when a player was actually pretty fast, our model predicted a fast time. And it did all of this based on the relationships that it found between the inputs of level and ammo and the completion time of our training data. That is so cool. And even though the predictions aren't always perfect, I think these are still really useful. And in terms of measuring how good the predictions were, with a regression task like the one we're dealing with here, the most common way to assess accuracy is using this metric known as R-squared. And since we brought in the functionality to calculate that using scikit-learn at the top of the code, this is really easy. So let's head back to the code. Now, to give a little bit more detail on R-squared, it is a metric that can have a value between 0 and 1, with a value of 1 being a perfect model. In other words, it got every prediction exactly right, all the way down to 0, which means a completely hopeless model that has no predictive power whatsoever. So let's take a look at how we did on this metric. And to do that, since we imported this at the top, let's put R-squared and then underscore score and parentheses. Then within the parentheses, let's pass it our yTest object, which are the true or actual values for the test set. And then after a comma, we also pass in the y_pred object, which are the predictions for those same players. So let's run this line of code here and see how we did. If we take a look down in our console, we see a value of 0.66, which is pretty good actually, so well done. And getting this accuracy or goodness of fit score is great, but I always like to think from a business or an application point of view. How are we actually going to use this, or what business problem is this model going to solve? Now here I think we've got something pretty cool. When new players come to this particular level or task in the game, we could predict how long it might take them. From a business point of view, there could be some really cool applications of this. Maybe we could use the prediction to challenge a player who is about to take on the task. For example, our model predicts that you will complete this level in 98 seconds. Do you think you've got what it takes to beat that time? Or perhaps we could use it to guide what they do next. If we know that there are levels which might take longer or shorter amounts of time, this might be useful information for them as they decide what they want to do next. Whatever we might use it for, let's just pause and recognize the fact that you have just built your very first machine learning model. So really, really well done. Again, go and tell your family and friends about this, as I know they'll be super excited about it. And I really want you to start seeing that this type of thing is within your reach. Sure, there are some complexities around building models that we didn't cover here. Things like making sure the data is fit for purpose, selecting the right features to include, tuning the model and putting it into production somewhere where it can receive data in the real world and make its predictions. But what we've done here truly is the meat of the machine learning process, and you did it. And trust me, you can do so much more than this too. So I didn't study data science or computer science or even mathematics, but I've had a very successful data science career working for a FAANG company. I've got 5 machine learning patents, I've written a book, I run a leading course. How can you do this as well? Come and join my completely free 75-minute session below where I cover all of this and more.